Over the next several minutes, we'll be discussing fundamental concepts for wireless communications links with an emphasis on the physical layer. In this module, we'll be looking at the building blocks of a wireless communications link. We'll discuss transmitters and receivers, including their subsystems, as well as functions of these devices. The communications channel has major impacts on communication system design and performance as well, so we will consider it also. We will also look at some basic properties of the signals that can be transmitted over wireless channels. In this course, we will limit our discussion to a single link between two radios, which is a special case of the general communication link shown here. This is an essential building block of all wireless communication systems and networks. We will consider some major subsystems and functions of wireless transmitters and receivers, as well as effects of the physical radio channel on communication. For those who are familiar with communication networks, this discussion will be mostly confined to the physical layer. In addition, we will consider ways of measuring performance of a wireless link, typically a radio link that transmits information that is inherently digital or information that has been converted to a digital form. And we will look at a fundamental limit on one of these performance measures. We will consider natural factors that limit wireless link performance, as well as other factors that are related to technology. A radio or wireless communication link includes a transmitter and a receiver. In this diagram, a source such as a video camera produces or supplies information to the transmitter, and a sink such as a video monitor consumes the received information. The transmitter converts information from a source to a signal that represents that information in a form that can be sent through a wireless channel and recovered by the receiver to be used or stored by the sink. The transmitted signal has properties that include power, center frequency, and bandwidth. Also, there are different ways of controlling the signal to represent the original information and to help the receiver recover the original information, even after the signal is altered by the channel. The receiver converts the transmitted signal that has undergone channel effects back to the original information, or an approximation of the original information. Here's a closer look at the transmitter. A transmitter converts information such as an analog message or a data file from an information source to a form that can be transmitted over a channel. The subsystems on the left can be special purpose hardware or software or firmware that runs on programmable or configurable signal processing hardware. The subsystems on the right are primarily hardware systems, although they can be made in a way that allows them to be controlled or configured by software. If the information to be transmitted is inherently digital, such as a data file, or if the information is to be converted to a digital form before transmission, as in the case of a digitized audio signal, a source encoder converts the information to a compact digital form. The goal is to reduce or limit the number of bits that are required to represent the information. If the data or the original signal can be compressed by eliminating or reducing redundancy, fewer bits will need to be transmitted to the receiver, and transmission can happen more quickly or more efficiently than it would otherwise. For example, many of the pixels on this slide are the same color as adjacent pixels, so it is not necessary to encode the color information for every pixel individually. Also, for digital signals, a second type of coding called channel coding adds redundancy to the signal. Why would we add redundancy if we just removed it? In this case, we are adding extra bits in a strategic way that makes it possible for the receiver to recover the original bits sent by the transmitter, even if some of the bits are changed by the channel. This is like a person repeating their speech in a noisy room so the listener can understand. A simple example is for the transmitter to send every bit 3 times in a row. The receiver can use a majority vote approach to recover the original bits as long as only up to 1 copy of the bit is corrupted by the channel. Additional possible operations include interleaving, which shuffles the bits in a way that helps error correction work better in fading channels, and grouping of data into packets that can be routed and processed independently after reception. A modulator converts either an analog signal or a sequence of bits to a form that can be transmitted. Most radios do this by modifying properties of a sine wave so that these properties or their changes represent information. For example, a signal voltage or bits that is to be transmitted. Sine waves have 3 properties: amplitude or maximum voltage, frequency, the number of oscillations per unit of time, and phase, the relative delay. And in the case of ultra-wideband radios that send brief pulses of energy, the time interval between the pulses can be modified based on the signal. In the case of a digital signal, the modulator output is in the form of symbols, which are time-limited segments of a modulated signal that represent a finite number of bits. A number of symbols can be transmitted consecutively, and such a sequence is called a frame and typically includes header information that tells the receiver how to process the signal. In the right column is the radio frequency front end. The radio frequency or RF front end is made up of devices such as mixers, filters, and amplifiers, and often includes one or more of each. A mixer changes the center frequency of the signal to a frequency at which effective transmission is both physically possible and permitted by any applicable regulations or policies. A filter allows energy at some frequencies to pass through with minimal change while suppressing energy at other frequencies. This is a way of cleaning up the signal before transmission so that the signal does not contain much energy at frequencies that would overlap with other coexisting signals. As with audio signals, an amplifier increases the strength or power of the signal so that it can be received clearly over a longer distance. Finally, a transmitting antenna converts the output signal of the RF front end into electromagnetic waves that travel through space. By radiating the signal in this way, the antenna enables communication with the receiver at some other location. A receiver converts the signal received after transmission through a channel to a form that can be used by an information sink. The subsystems on the left consist of special purpose hardware that can be designed in a way that makes it possible to control it or configure it by software. The subsystems on the right can be implemented as signal processing software or firmware that runs on programmable or configurable processing devices, or as special purpose hardware. The receiving antenna converts a received electromagnetic wave or time-varying electromagnetic field into a time-varying voltage or current that can be processed to recover the original transmitted information. The RF front end of a receiver performs operations similar to those performed in a transmitter, but in the reverse order. Also, the power levels in the receiver are much lower than those in the transmitter. The demodulator reverses the operation performed by the modulator in the transmitter. That is, it converts the received signal back into bits. For now, we are ignoring synchronization, which is a complex and challenging yet essential process, particularly for digital receivers. Precise synchronization is needed to enable the receiver to match the transmitter's frequency and phase within a narrow tolerance that enables the receiver to demodulate the signal accurately. Synchronization is also essential because it allows the receiver to keep track of transitions between consecutive symbols and bits. The channel decoder corrects bit errors caused by the channel if there are not too many consecutive bit errors. The source coder, or the source decoder in this case, undoes any compression or analog to digital conversion to recover the original digital or analog signal. As in the transmitter diagram, we are ignoring deinterleaving and depacketization as well as framing. Between the transmitter and receiver is the channel. In general, a channel could be a cable or even a recording medium such as a hard disk or SSD, or a video or audio disc. For the purpose of this class, we are interested in radio channels, which include free space, similar to a vacuum, terrestrial, air-to-air, air-to-ground, and others. The channel makes communication possible, but it also makes communication challenging because it changes the transmitted signal. The signal power decreases over distance because the transmitted energy spreads over a larger surface at larger distances from the transmitter. The signal will experience a delay that is proportional to the transmitted distance, and additional effects are caused by both natural and human-produced aspects of the environment. Depending on the channel, the signal may undergo other effects that make it more difficult to receive. These effects are caused by objects between and around the transmitter and receiver that could include terrain, vegetation, buildings, vehicles, and water or gas molecules, as well as by motion of the transmitter, receiver, and objects in the environment. Channel effects include fading or variation in received signal strength over time and space that is related to motion of the transmitter, the receiver, or objects in the physical channel environment. Another effect, called inter-symbol interference, which occurs when two or more copies of the signal reach the receiver after traveling by separate paths and experiencing different delays. This effect is like hearing a loud echo at the same time as the sound that you are listening for, and makes it difficult for the receiver to recover the transmitted signal accurately. Radio signals can also experience Doppler shift, like the change in pitch in an emergency vehicle siren that you may hear as the vehicle moves past you. In the same way, the frequency of the radio signal heard by the receiver will change if the distance between the transmitter and receiver is changing. In mobile channels that have multiple paths, a Doppler spread results from variation in the rate of change of the various path lengths. A common way to measure performance of a digital communication system, including one that transmits data over wireless link, is to measure the system's data rate, for example, the number of bits of data that are transmitted and received per second. This measurement is also called the throughput of the system. Closely related to data rate or throughput is the concept of capacity, which is the theoretical maximum rate of information transfer, typically as a data rate or throughput that channel can support. For the receiver to receive the signal after the signal has passed through the channel, that received signal must be sufficiently strong compared to two sources of undesired energy. We will discuss those sources in the next module. Radio signals carry information over a channel. A radio signal has several properties that will be of interest for this course as well as in other courses in the series. Anyone who has used an AM or FM broadcast receiver has encountered the first property, frequency. This is the number of oscillations or changes in polarity of an electromagnetic wave during a unit of time. These changes occur in cycles. For example, the electric field at a particular location changes from one polarity to the opposite polarity and then back to the original at regular intervals over time. 1 hertz, written uppercase h, lowercase z, is 1 cycle per second or 1 oscillation per second. Radio frequencies are in the range of thousands, millions, or billions of hertz typically, so we often use the corresponding prefixes and the units kilohertz, megahertz, and gigahertz. Hertz are also used to measure the range of frequencies that a signal occupies, the upper frequency minus the lower frequency. The signal bandwidth is not always obvious from looking at the frequency plot or spectrum of the signal, but to show the concept in the figure at the bottom of the slide, we are using a signal that has a nearly rectangular frequency spectrum. A signal also has a corresponding power level, but the power is spread over the signal bandwidth, so the vertical axis in our figure is power spectral density, or power per unit of bandwidth, for example, watts per hertz of bandwidth. And in our simple example, where the signal is nearly rectangular in the power spectral density versus frequency plot, we can get a close approximation of the signal power by multiplying the signal's power spectral density by the signal bandwidth. The minimum level of the power spectral density shown in the plot outside of the signal bandwidth is caused by a phenomenon known as noise that we will discuss later. This module has presented an overview of a wireless communication link. We looked at transmitters, receivers, and their functions and subsystems. We also considered wireless channels and measures of performance for digital wireless links.